Hi there and welcome to this video for Senior Physics. In this video we're going to look at Kepler's three laws of planetary motion. Now, Johannes Kepler was a German astronomer who moved to Prague to work with Tycho Brahe. Now, if you remember, Tycho Brahe was a fantastic data collector. He had produced his quadrant and was mapping or making extensive detailed observations of the positions of the stars in the night sky. Because Tycho Brahe worked with for Emperor Rudolf as his astrologer, they had access to a huge amount of capital, which allowed their studies to occur. Now, after Tycho Brahe's death, Kepler tried to start explaining a number of observations, and one of the big things that he wanted to talk about was the Mars loop that we talked about in the timeline. This is where the idea that Mars, which can be seen from Earth, seemed to make this backward shift in its orbit. And for years, the Greeks kept working on the idea that all of the planets followed a circular orbit, but could not allow for this observation to be explained. So Kepler set out to actually produce some calculations which would allow him to explain this loop for Mars. Now, so obscure were his writings that Galileo once wrote, so obscure that apparently the author did not know what he was talking about. Now, Galileo and Kepler were living around the same time, and it wasn't until as far as I know, round about 5 to 8 years, that Kepler actually produced his first breakthrough. And this was due to him actually throwing out his data because he couldn't make the circular motion fit, and accepting Tycho Brahe's observations that they were concrete. It's one of the first opportunities where we've actually had a case where the data has driven the conclusions rather than the other way around. So what he noticed was that he threw out his conclusions for a circular orbit and worked on the idea of different shapes. And basically what he came up with was the idea that the planets moved in ellipses. And this was his first law. And basically, when he published this work, this produced emphatic evidence that we had to deal with an Earth-centered universe, which was first put forward by Aristotle and Ptolemy. So the three laws that were put forward were the laws of orbits, the law of areas, and the law of periods. Now, basically, the first law of orbit basically states that planets have elliptical paths with the sun at one focus. So here you can see there's the sun and there's the planet, but instead of being in the center, the sun is off to one side. And again, this goes against the Ptolemaic theory of circular orbits put forward by Aristotle as well, the idea that you've got a circle and then the planets spin around the Earth. Okay, so you've got the Earth in the center and the planets on the outside. Now, for you and I, this isn't a major, but at the time when Kepler was alive, this is a major conclusion to draw. Now, his second law is the law of area. And basically, it states the following: the speed of a planet along this path is not uniform, but varies with its distance from the sun in such a way that a line drawn from the planet to the sun would sweep out equal areas in equal times. Or, in other words, the area swept out in a given time by the radius vector is always constant. So what he's basically stating here is, if we look at this model here, we've got the planet in green revolving around the sun. As it approaches the letter R and then moves to S, it's going to start speeding up. Now, it's a bigger area which is generated there, so it's going to move faster. So it's going to cover a larger area, but it's actually going to cover exactly the same time that it covers when it goes from L to M on the other side, sweeping out again the same area, but it's over a smaller distance. With it being over a smaller distance, it's going to have less speed, but the time period, because there's less speed, will be directly related to how far it is from the sun. So both A and B will take the same time, but in order for that to occur, the movement from R to S has got to be a lot faster than the movement from L to M. In each case, we're going to have exactly the same area which is going to be created. So that's his second law, that basically equal areas will actually be swept out with the same time, but it's going to change the speed at which this occurs. Now, his third law basically is more of a mathematical law, which basically states that for orbiting satellites or planets of any system, the ratio of the radius of orbit cubed, r cubed, to period squared is constant for all satellites of all systems. So basically we've got this formula that r cubed divided by t squared is going to equal a constant. It's going to be the same for every single planet. Okay, so we would be able to take their radius and their time period, and they would come up with roughly the same values. Between two planets or satellites, we then have this situation where on one side we've got the third law for planet A, and on the second side we've got the third law for planet B. They should equal each other, or within a very small range. And here we've got some idea of what's going on. You can see here we've got Mercury has a radius of 5.97 times 10 to the 10, and the period of revolution is 7.6 times 10 to the 6. If we do r cubed over t squared, it's 3.68 times 10 to the 18. Now compare that to Venus, which has a different radius and a different period. You can see it's virtually the same figure. So hence r cubed over t squared is going to equal a constant for any planet. So let's have a look at a quick example. So here we've got an example of Triton and Nereid, which are the two moons of Neptune. Triton is 353,000 kilometers from Neptune and has a period of 5.87 Earth days. Nereid is 5,560,000 kilometers from Neptune. It has a period of 359.9 Earth days. We're going to find out if these days are consistent with Kepler's third law. We know that Neptune has a radius of 24,750 kilometers. So let's work through. So we look at Triton to start off with, and we've got its distance. So its distance basically is going to be taken into the distance from Neptune as well as the radius, divided by the time it takes. Now what we've done is taken out a factor there, so we've got 5.87 squared, because we've got days in each case. So we've got 5.87 squared days, that's our time period, and we've got our radius, which is the distance from Neptune to Triton, and we get 1.56 times 10 to the 15. Then we do exactly the same for Nereid. Nereid basically 5,560,000 plus its radius, and which is the radius of Neptune, and basically we've got 359.9 days. So again we square it. Now you'll notice here that the values 1.34 times 10 to the 15 for Nereid is virtually the same as it is for Triton. So as our conclusion is, because these values are very, very close, Kepler's law can hence be confirmed. Okay, well I hope that makes sense to you. So hopefully that makes you can work on these, but don't just take my word for it. Take the word of Carl Sagan. He was a famous astronomer, TV presenter in the 70s, who put forward a series of very, very informative videos. And this is what he said about Kepler.
Having cleaned the stable of astronomy of circles and spirals, he said, he was left with only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer. And months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully. In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this: a planet moves in an ellipse with the sun at one focus. As the planet moves along its orbit, it sweeps out, in a given period of time, an imaginary wedge-shaped area. When the planet is far from the sun, the area is long and thin. When the planet is close to the sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same. This provided a precise mathematical description of how a planet changes its speed in relation to its distance from the sun. Now, for the first time, astronomers could predict exactly where a planet would be, in accordance with a simple and invariable law. Kepler's second law is this: a planet sweeps out equal areas in equal times. Kepler's first two laws of planetary motion may seem a little remote and abstract. All right, planets move in ellipses and they sweep out equal areas in equal times. So what? It's not as easy to grasp as circular motion. We might have a tendency to dismiss it, to say it's a mere mathematical tinkering, something removed from everyday life. But these are the laws our planet itself obeys, as we, glued by gravity to the surface of the Earth, hurtle through space. We move in accord with laws of nature, which Kepler first discovered. When we send spacecraft to the planets, when we observe double stars, when we examine the motion of distant galaxies, we find that all over the universe, Kepler's laws are obeyed. Many years later, Kepler came upon his third and last law of planetary motion, a law which relates the motion of the various planets to each other, which lays out correctly the clockwork of the solar system. He discovered a simple mathematical relationship between the size of a planet's orbit and the average speed at which it travels around the sun. This confirmed his long-held belief that there must be a force in the sun that drives the planets, a force stronger for the inner fast-moving planets and weaker for the outer slow-moving planets. Isaac Newton later identified that force as gravity, answering at last the fundamental question: what makes the planets go? Kepler's third, or harmonic law, states that the squares of the periods of the planets, the time for them to make one orbit, are proportional to the cubes, the third power, of their average distances from the sun. So the further away a planet is from the sun, the slower it moves, but according to a precise mathematical law.
Okay, so I hope you found that interesting. Hopefully Carl Sagan puts it into a more dramatic process than I did. But again, these are the three laws that you need to learn with respect to Kepler. This is what his contribution, and really his contribution was fundamental in our understanding for planetary movement. Okay, so I hope you found that useful. I will put up some worksheets that you might be able to utilize for working through Kepler problems, and I look forward to you meeting me again. So thank you for watching, and bye for now.